want solutions, you must focus your mind. Introducing your host, Mason Hargrave.
This week, I have the pleasure of sitting down with David Schwartz, the author of The Last Man Who Knew Everything, The Life and Times of Enrico Fermi, Father of the Nuclear Age. Enrico Fermi is one of my favorite physicists, and so it's extremely exciting to get to sit down and have a chat with someone with such an in-depth knowledge of this fascinating character from the history of science. Without further ado, I introduce to you David Schwartz. So how is it that you decided to write an entire book is a big undertaking.
Yes.
So how is it that, what happened that snapped where you went, I'm writing a book about Enrico Fermi?
Well, first of all, you should know I've written 2 other books before this. So I know, actually, if I'm honest about it, I've written 4 books.
Okay.
2 of which were nonfiction and were published.
Right.
And 2 of which were fiction and were not published.
Oh, interesting.
So I've written 4 books. So I know what it's like to sit down and crank out
page after page.
And you sort of get into a zone where the words start to come. What specifically persuaded me to write the book about Fermi was, I tell this in the preface to the book, my father was a particle physicist, as you know.
Not just a particle physicist. He was a Nobel Prize winner.
Yes.
You probably get tired of saying that.
No,
I have to say it for the point of the audience to understand.
I understand. So he died in 2006.
Mm-hmm.
And we gave all of his books to the Bronx High School of Science, where he was a student in the 50s, late 40s, early 50s. And then in 2013, my mom called me up and said, I have all these papers of his in the garage. They're in a filing cabinet. What should I do with them?
Right.
And I said, well, why don't you send them to me? I'll look through them and I'll see what's what and figure out what needs to be done with them.
Right.
And I was going through those papers and found an essay by a physicist who was a very good friend of my dad's named Val Telegdi, who was a professor first at the University of Chicago and worked directly with Fermi, and then was a professor at ZTH in Zurich.
Right. Very prestigious school.
Yes, very prestigious.
Really, the MIT of the MIT
where
of
Einstein taught. You know, it's
Europe.
It's a very, very good school, and he's a brilliant physicist. He died in 2006, a few months before my dad.
Mm-hmm.
And Val had this lovely essay about Fermi's time at the University of Chicago.
Mm-hmm.
And, I knew a little bit about Fermi, but I didn't know a lot. And what I didn't realize, I knew he had created the first nuclear chain reaction. I knew that he had been involved in the theory for beta decay, but I didn't know that he was such a great teacher. And so I was fascinated by reading all of this. And I thought, well, I should learn more about Enrico Fermi. And I went to the library, and to my absolute amazement, at that point, and this is 2013, the most recent biography of Fermi in the English language was by Emilio Segre, his great student, and it was published in 1970.
Wow.
And I thought, that's ridiculous. Well, I got the book out of the library. I read it. It's a very good book. But I thought, he needs a new biography. So I decided to sit down and write it. And my wife, Susan, to this day, says, I had no idea what you were thinking of until you came home one day and said, well, I have an agent for the book. And she says, what book? And I said, the biography of Enrico Fermi. She says, who's Enrico Fermi? And it went on from there. But
Carl Jung has this interesting idea that you get possessed by the need to make something. And that's how any book gets created. It's some sort of possessed nature of just, this has to happen somehow.
Absolutely. And so, so the process, went on from there. Part of the challenge was catching up with the living graduate students of Fermi.
Right.
Who were all in their mid to late 80s, early 90s. And, I did end up speaking with, I think, 6 of them.
Who all, any notable names out of that group?
Well, T.D. Lee, Dick Garwin, Jim Cronin, Art Rosenfeld, Jack Steinberger. I'm sure I'm missing one or two others.
Right.
And, well, what's amazing about Fermi is that 5 of his direct graduates, Jerry Friedman as well, up at MIT, 5 of his direct graduate students won Nobel Prizes.
Right.
And some in theory and some in experiment, right? Because Fermi himself was both a great experimentalist and a great theorist.
Right.
And he, that's unique. Rutherford had a similar number of Nobel Prize winning graduate students, but they were all experimentalists.
Right.
Sommerfeld in Munich had a similar number of Nobel Prize winning graduate students, but they were all theorists.
Completely.
But Fermi trained, Nobel Prize winning experimentalists and Nobel Prize winning theorists.
Right.
And just unique from that point of view. And it was one of the fun things was meeting these people. Some of them were old friends of my dad's. Steinberger, of course, was a very close colleague of my father's.
And this actually must have been a big advantage to you being able to write the book, which is that you had the right pedigree to be able to call and say, hey,
yes.
And actually get in the office with these people who otherwise,
probably wouldn't have given me the time of day.
Right.
But Jack Steinberger knew me from the moment I was born, basically.
Right.
Dick Garwin knew me from the time I was born. I mean, these are people who, I knew ever since I can remember.
Right.
And so they were happy to help out. And they also loved their time with Fermi and were happy to talk about it. People asked me, was it challenging to write about the physics? And, I have to say that my publisher and I decided early on that it was not going to be a physics book.
Right.
It was going to be a biography about a physicist. And to the extent that I had to get into the physics, and you do have to get into the physics, it was going to be accessible to the lay reader.
Right.
And I worked very hard on that, and I was fortunate to have 3 professional physicists working with me to help me understand things and understand the right way to express them.
Right.
There were times when I really found some concepts challenging. I found the Fermi Dirac statistics concept really challenging.
Right.
Until I read a passage by Hans Bethe, who was once again very good friends with Fermi.
That's a big name in and of itself.
Yeah, and Bethe explained, what was important about Fermi Dirac statistics, and so all of a sudden it clicked, and I just quote Bethe, in that. The implications of Fermi's work is that at absolute zero, the atoms are still moving because they have to move in order so that they don't occupy the same quantum space.
Right.
They're jostling for position. They're lining up, spin up, spin down, and lining up in energy states, even at absolute zero.
Even at absolute zero, yeah. There's still
there's a quantum shuffling that goes on.
Sometimes it's called the highly degenerate ground state.
Right.
Meaning
exactly.
there's turns out that absolute zero is the lowest energy you can get, but even that isn't nothing.
That's right. That's exactly right. That's exactly right. That's fascinating.
It's odd. It's not what you would expect because it's not what they tell you in elementary school.
That's exactly right. And
it turns out a lot of the hardest concepts to get in physics are ones that you actually have to relearn because someone along the line told you something that wasn't quite right.
That's exactly right. But later on, I read. This was after after I published the book. But later on, I read there was a woman who I believe was a professor out in California who passed away very young, and she had done a number of experiments with bosons and fermions at extremely low energy.
Right.
And she reported that you could see, at temperatures that really are very, very close to absolute zero.
Millikelvin scale.
The fermions begin to sort of line up, in this two fermions, one spin up, one spin down at each energy state.
Right.
And you can begin to see the actual results of the exclusion principle.
Right.
And it's just amazing.
So what is can you maybe, because for the lay audience, what is the exclusion principle? And we don't have to get super, we're not trying to get super heady with it. We're trying to remain at a.
Well, one of the things that was discovered experimentally was that when electrons that are associated with an atom around a nucleus of an atom, it seems that no orbital can share more than 2 electrons.
Right.
Okay. And the question is, why is that? And based on some odd experiment, you notice that in a magnetic field, the spectrum of an atom, sort of all the spectroscopic lines double.
Right.
And a guy named Wolfgang Pauli, who was a brilliant theorist, spent a lot of time thinking about why that would happen. He ended up thinking that there must be 4 quantum numbers that every electron has: position, momentum, third one I can't remember, and spin. And he didn't even call that 4th number spin. He didn't believe in spin at the time. But what he said was that a magnetic field separates out by spin, and or by that 4th quantum number. And so Fermi took that idea and applied it to atoms in a gas.
Right.
And was able to describe a gas from a statistical mechanics perspective or a thermodynamics perspective,
right,
using the exclusion principle. So the basic thing to remember is that if you have a fermion, an object with a 1/2 spin,
which an example of which, what would be a common example of a fermion?
Electrons, protons, neutrons, many atoms themselves, not all atoms, but
electrons are fermions.
Yes, electrons are fermions.
Yeah.
Electrons, protons, neutrons, quarks are fermions. But photons, light particles,
right,
are not. They're bosons.
Right.
So photons can exist in the same place at the same time with all the same quantum numbers, but fermions can't.
Right.
And 99.9% of the world is fermions. And so, when I push my finger on here, a lot of this is the electromagnetic force that's pushing back. But there's also something else going on, which is that, the subatomic particles cannot exist in the same place at the same time.
Right. Right.
And so you get this exclusion principle.
They can't compress into the same quantum volume.
Right. Right.
And it turns out to be like what all interesting chemistry comes out of this fact.
That's exactly right. That's exactly right. And it explains, largely explains why some atoms bond and some atoms don't.
And what the periodic table is all about.
And exactly what the period. So when all the electron orbitals in an atom are full, it's very hard to bond. But when there's an electron missing in one of the orbitals, now you can
get things close to each other.
That's right, exactly.
Because no longer does the exclusion principle apply, because you have a spin up and a spin down, and they can match up and get married,
exactly,
and that turns into your chemical bond.
Exactly.
So
anyway, I spent time trying to develop concepts like that.
Right.
Develop the theory of beta decay, which is sort of the basis for 20 or 30 Nobel Prizes since then, including the Higgs boson, because Mr. Higgs thought about the idea of the Higgs field and the Higgs boson as a result of some theories about the weak interaction and the weak field.
Right.
And why does the boson that carries the weak interaction have mass? Because it shouldn't really have mass, but it's very, very heavy compared to some of these other particles. And that's where the idea of the Higgs field came.
Is where does the mass come from?
Yeah, right. It's not where all mass comes from. I mean, that's one of the mistakes that popular science makes. The Higgs field is where the mass of certain interactions comes from. So,
Yeah, particle gets out of my wheelhouse very quickly, because I'm used to the statistical view on things, and it's interesting to hear that what Enrico really did was like married these
he loved statistical mechanics. He
Right.
absolutely loved it.
Right.
And kept on coming back to it time and again. He was fascinated with the concept of entropy. And in fact, the motivation for the statistics was a feeling that entropy, which was a classical concept at the time,
Right.
should be able to be understood through quantum ideas.
Right. There should be some sense of quantum entropy.
Right. And that's what drove him to do that.
Makes sense. And it's always interesting to try to figure out. I think one thing I keep running into in physics in general is whether do you come up with the classical theory first and then try to quantize it, or you try to come up with the quantum theory first and try to blow it up and generalize it to the classical.
Well, I mean, in history, of course, everything started out as classical, and then the quantum theories arose really almost entirely because of experimental results that couldn't be explained. I mean, the original idea for the quantum came from industrial experiments that were being done in Germany,
right,
where they couldn't understand why certain results, black body radiation, wasn't behaving the way they expected it to.
So this whole podcast ends up being about solutions and the art of problem solving.
Right.
And of course, there's kind of one of the classic phrases, I think, of Newton solving a problem. I can't remember what mathematician put it forward. It was the isochrone problem. And this, I can't remember which mathematician who did put out this problem, but he said, well, I came up with a solution to this problem. If anyone, I dare any other mathematician to come up with a solution to this problem. And somehow this ends up on Newton's desk, and Newton just gets obsessed and solves this thing in a day, and sends back the letter. And the writing about getting this, this letter from Newton was, I recognize the lion from the mark of his claw. Meaning he didn't even address it as Newton. He just sent in the solution. Newton was so just bored of this problem that no one else is solving.
That's very interesting.
And because he could tell the problem solving method was very Newton. So I wonder similarly if through going through Enrico's work, what did you find in there that might be?
There's a very first. Let me tell you an anecdote about his problem-solving abilities. He was on a train ride with a guy named Arthur Compton, who was the head of the University of Chicago lab during the Manhattan Project.
Right.
And Fermi, during this period, reported to Compton. Compton was a brilliant physicist. He had won a Nobel Prize for his work on X-rays, experimental work on X-rays. And Compton was explaining to him that he had been skiing in the American West, and that his watch, when he was up on the top of the mountain, his watch was giving him very poor time. But when he got back down to sea level, it was fine again. And he said he struggled with it for about 3 or 4 days, but finally came up with the answer. And he was wondering if Fermi could figure out why the watch was giving bad time. And Fermi took out a piece of paper and a pencil and solved the problem in about 2 minutes.
And what was the solution?
That is not discussed in the anecdotes, but I would imagine it has to do with the drag on the balance wheel at higher altitudes versus lower altitudes.
Interesting.
I mean, because there's less drag at higher altitudes.
Oh.
It would run faster. I think, there's
I had a couple ideas. I thought metal expansion, maybe if it was colder at the top than the bottom, and
that could be it too.
It was something to do with.
The thing is that the anecdote is told, but there is no analysis behind it.
The understanding just being that he came up with an answer. Took 3 days.
But Fermi's way of solving problems was very different from a lot of others. He always tried to solve problems quickly to an order of magnitude. And beyond an order of magnitude, he got very bored.
Right.
So what he would do is simplify a problem to its essential components and do estimates about what the solution was. And once he had estimated the solution to within an order of magnitude,
without a multiple of 10 for those at home,
right? Within a multiple of 10, he was quite happy with the result.
Right.
So, great example. The night before the first atomic bomb explosion in New Mexico, in the deserts of New Mexico, he sat down and wrote out a little bit of an equation about that related the blast wave to the yield of the bomb.
Mm-hmm.
And then when the test took place, he scattered some shreds of paper into the blast wave, measured how far those pieces of paper moved, and announced to everybody around him, oh, that was a 10 kiloton blast. And it turned out to be about 16 kilotons, which was from Fermi's point of view,
got it right.
So that was the way he was. So it could be frustrating and sometimes infuriating for physicists who grew up in a different school of thought where the precise answer was really important, where working on the problem to the very, very, to the 7th or 8th decimal place was really important.
Right.
He had no interest in that and got bored very quickly once he had set up the problem and solved it to within an order of magnitude.
And turns out this is a super useful way to think if you're not working in very simple systems.
Yes.
Because once you're working in a complicated system, you're not going to get that. You're not going to get that 7th decimal precision.
Right.
And you have to be willing to let that go. And if you're not willing to let that go, you're not going to be able to work in fields like biology, and you're certainly not going to be able to work in fields like astrophysics.
Exactly. And so he had this way of looking at problems where he would just strip out all the complexity, try to get to the very heart of what was going on, focus on that to the exclusion of all the other complications, and then that would be what he would bring to the table.
Right.
He was, contrary to what people might think when they realize what he accomplished, he was a very slow thinker. He was very, very slow and very methodical, but nothing could stop him. So he was likened to a steamroller that moves very, very slowly and crushes everything in front of it.
I like to hear that because I think one of my struggles in undergraduate was that I was a very slow thinker. And I always joke that I was an engine with low speed, high torque.
Well, that was Fermi. Fermi was exactly.
I'm not comparing myself to Fermi here. No, I just like to know that there are successful people out there.
Well, I mean, if you're a slow thinker but unstoppable, that gets you part of the way there. The other secret that Fermi had was that he had virtually inexhaustible reserves of energy.
Yeah.
So he would think about stuff all the time. And he had no interest in anything else.
Right.
I mean, no interest in history, no interest in art, no interest in philosophy, no interest in literature, none of that.
Yeah.
All he was interested in was physics and the outdoors. He loved being in the outdoors and hiking and stuff.
There's a lot of hikers in that Manhattan Project team.
Well, he was one of the biggest ones. He definitely was one of the biggest ones. But he and Bethe and Oppenheimer was a big hiker. And
interestingly, and I'm putting this out here, just kind of my own curiosity. So another really excellent biography in science that I read recently was Chaos by Gleek.
Yes,
who goes through Mitchell Feigenbaum
yes.
and Leo Kadanoff, who I'm
yes.
academically related through both through my professorial advisor.
Yeah.
Or my PhD advisor, and I'm wondering. So, and Feigenbaum also came out of that milieu, out of I think what is it? Not Lawrence Livermore.
Los Alamos.
Los Alamos.
Yeah.
In New Mexico.
Well, Los Alamos was, speaking of chaos, and Fermi, Fermi did one of the very first simulations of a physical process in a computer.
Is this the Fermiac?
Well, no, he did not. It wasn't the Fermiac, although Fermiac was a computer. It was an
analog computer.
Yes. But this was a digital computer. It was called the Fermi Ulam Pasta Singu paper, which simulated the vibration of a string. And it turns out, and they introduced a nonlinear element to the equations. And it turned out that it displayed, Fermi thought that the results would be relatively random. Over time would be completely random. It would behave in an ergodic fashion.
Right.
Okay. That it would eventually, sort of every state would be occupied.
Which to clarify for the people at home, that is what ergodic means.
Right.
Well, you just said
every state would be occupied. And so what he discovered was that there was, in fact, there were complex patterns that developed. And so it wasn't really quite ergodic.
Yeah.
And it surprised and amazed him. And it surprised and amazed a lot of people. But that paper is considered one of the foundational papers in chaos theory.
Yeah.
But
before the word came out.
Of course. But to get back to your first point, which is that, everyone in Los Alamos loved the outdoors.
Right.
If you were there for a summer, if you were there for a year, you just went hiking in the Jemez Mountains. And just
what was it about Los Alamos that produced probably the funding, but what brought, because there's a few places I can think of in history where you have this culture. Bell Labs in the 80s, Los Alamos in the 40s, 50s, 40s and 50s. There's a few places where you see this sort of thing happen.
Yeah.
And what causes that?
It's sort of magic. I think you can try to plan for it, but it depends very much on the people.
Yep.
I think the basic solution is find the right people and put them together, and they'll make magic.
Do you think there's a modern equivalent?
Today, right now, it's really, really hard. I would say that in the 80s and 90s, I would have said something like Xerox PARC. Bell Labs was still doing good work up to then. IBM Watson Lab.
Yep.
The Institute for Advanced Studies at Princeton, although that tends to be much more theoretical, much less practical bent.
Right.
These days, I can't think of anything off the top of my head that compares to it. But the world is so very different, and look, we're living through a period where we may not ever feel like we need to go back to work. Right?
Yeah.
When I say that, I mean back to the office.
The only things I can think of are like Google Applied AI or Amazon, strangely enough, being these places where a lot of this sort of research comes out.
Yeah, and I don't know the culture of those places well enough to know whether you really are encouraged to blue sky your thinking.
Can you talk about that? Because I think that was a unique feature of Los Alamos and some of these other research institutions.
Before the war, that wasn't, because before the war there was only one
project. It was the Manhattan Project.
But after the war, people were given a huge amount of leeway to pursue things that seemed interesting, and the government was happy to fund it. And I think that people were much less interested in the practical application of what they were doing than they were in whether these were interesting challenges in and of themselves, sweet scientific problems.
Right.
And there are some equivalents in the world of biotech and bioengineering. For example, I got to know through my father very, very briefly a fellow named James Black, Sir James Black, who was a Scottish pharmaceutical developer who developed Tagamet and developed beta blockers.
Mm-hmm.
And, he was asked, in an interview with, I think in the FT, what motivated him to do this, because he didn't make any money on it. He was salaried employee of the Wellcome Foundation for part of this, at least. And he said these were just sweet ideas. These were sweet, scientific ideas that seemed like a lot of fun if you can solve them.
Right.
You have a sense of what regulates heartbeat. Can you produce a chemical that can control that?
Right.
You have a sense of what produces acid in the stomach. Can you produce a chemical that can turn that on and off? And, here you go.
Here you go.
Yeah.
It's so, and then.
Which gets right back to your issue of solutions, right? Because I do believe there is such a thing as an interesting scientific problem. I believe that.
What makes a scientific problem interesting?
I think it has to do with the way it relates to other problems. I think, scientific problems don't get solved out of the blue, and they don't arise out of the blue. But certain types of discoveries take place because someone is thinking about a lot of different things together.
Right.
And is thinking about the relationship between all those different things. And then comes to a solution to a particular problem that leverages a lot of different insights into a lot of different other problems. And I'll come back to Fermi on this, okay? So, and Fermi was very good at doing this kind of problem solving. He takes Pauli's exclusion principle and creates, a way of looking at statistical mechanics that way. He takes Dirac's theory, quantum electrodynamic theory, the theory of how an electron behaves in a quantum field. And he thinks to himself, can I use that idea of a quantum field to solve one of the real puzzles of 1930s physics, which is what is going on in beta decay? A beta decay is a radioactive process where the nucleus of an atom gets so crowded that a neutron jostles up against a proton and becomes a proton. And in the process of becoming a proton, the neutron creates an electron and a neutrino instantaneously, and they get ejected out of the atom.
In order to maintain conservation of charge.
Conservation of charge and conservation of energy.
Right.
Okay, the electron gets created for conservation of charge, and the neutrino gets created through conservation of energy. Okay?
Right.
So the neutrino is really just it's an accountant's trick. That turns out actually to be real. But it was Pauli who thought, the problem with beta decay was that it seemed to violate
conservation of momentum?
Conservation of energy.
Oh, of energy.
Energy. Because if you took a look at the energy profile of the electrons that were coming out of beta decay, they were all over the place.
Oh, interesting.
The energy spectrum of the electron in beta decay is very wide.
So where's the rest of the energy? It has to be tight.
So it should be tight because if the energy is low, where is the missing energy going? When because we know that it can come out with very high energy.
Right.
So what's going on? And so it was Pauli who had the idea that there's a particle that we're not seeing because it's neutral, and it must be very, very light because it doesn't interact. And Fermi thought, well, I'm going to use Dirac's field theories to create a field theory of beta decay.
Mm-hmm.
And he laid it out, and it turned out to be almost exactly right. Almost exactly right. I mean, his theory was that the neutron and the proton actually bump into each other and create this interaction. They don't quite bump into each other. They come very, very close. And then there's an exchange of bosons between the two, the double E or the Z boson,
Right.
that actually creates that creates the transition from neutron to proton, or from proton to, I can go backwards too, go from proton to neutron.
Right.
So, so Fermi was using someone else's idea that was created in a completely different context to figure out a sweet problem that had been troubling people because it seemed to violate what they saw seemed to violate some major principles of physics.
Right.
Give you another example of a problem that's sweet, and a solution was solved. In 2000, I believe 11, there was an experiment called the Gran Sasso experiment in Italy, where they were shooting a neutrino beam from northern Italy through the Alps to a detector somewhere on the other side of the Alps. And when they did the measurements, they came to the conclusion that neutrinos were moving faster than the speed of light, which is
spells trouble for Einstein.
Which is a total violation of some of the central principles of theories that physicists hold very dear.
Mm-hmm.
And so people were running around with their hair on fire. And eventually what happened was they went through the experimental equipment and discovered that they had miscalibrated something in the experimental equipment. So it was an error that way, which led to a lot of people breathing a sigh of relief. But so sweet problems come up because they're related to a lot of different issues. I mean, imagine if neutrinos had been moving faster than the speed of light, imagine how much physics would have to be rewritten.
I think around the time when we weren't sure yet that the Higgs boson existed, Stephen Hawking bet against the existence.
That's right.
And he was asked why. He says, well, because none of the interesting things happen when things line up with their expectations.
Exactly. And
so it's these anomalies that you find that are actually interesting. It's when things don't quite meet.
And the more central the anomaly, the more impact it would have on, a broad range of physics phenomena.
The more that has to be rewritten.
Exactly.
And so it's in some sense, it turns out to be the more that has to be rewritten, if this turns out to be true or false, is what makes a problem interesting or more or less interesting.
Exactly.
In math, of course, there's actually even an example of this, which is I believe the where, oh gosh, I'm going to forget the name of the principle as soon as I start to talk about it. Oh gosh, it is the it's a conjecture right now. It's not Fermat's last theorem that was proven. Well anyway, it has to do with where the primes lie on
the Riemann hypothesis.
The Riemann hypothesis. Thank you. And tons of modern mathematics is written assuming the Riemann hypothesis is true. And if the Riemann
because it seems true.
Well, but that's never a good argument as a mathematician.
In math, that's a
terrible argument. And so and that's why the Riemann hypothesis ends up being an interesting problem, is because tons of modern math depends on whether or not it's true.
Yes.
And that's why chaos turns out to be interesting, is tons of dynamical systems that we thought we understood could not possibly be understandable in the way that we were trying to solve them. At the time, around the 1970s. And so it sounds like Fermi was on track with a number of problems of a similar.
He always had a knack for settling on problems that were interesting. He was very interested toward the end of his life in an experimental project where he shot protons from a cyclotron into the nuclei of atoms to see how they bounced around, and came to a conclusion. Well, he saw something called I think it's called the delta resonance.
Mm-hmm.
And which is a sort of a state of a particle that suggested to people that protons and neutrons might actually have an internal structure. And so,
by which you mean
quarks and gluons,
yeah.
Right? But it was way early in the process, and no one had thought about this deeply, and it took another 10 years before people began to really hone in on that idea. But those first experiments that Fermi did, Fermi was very, very aware of what sort of the cutting edge issues were, and always gravitated to those. And as a result, did a lot of. I mean, here's another great example of something that fascinated him. Cosmic ray. I mean, you'll know this. Cosmic rays sometimes come into the Earth at enormous energy levels. Enormous. I mean, they pack the momentum. An electron or a proton can pack the momentum of a Mack truck. That's how fast they are going.
Mm-hmm.
And they and so the question is, where do they get all this energy? They're going 99.999999 the speed of light, just below the speed of light. And so where do they get all this momentum, all this energy? And Fermi had a series of conversations with astrophysicists he knew, and came up with the idea that they're accelerated through vast intergalactic magnetic fields. That there are these big magnetic fields that basically serve as accelerators for cosmic rays that come out of stars or some other kind of stellar phenomenon, and then just get whipped and whipped and whipped and whipped over hundreds and thousands of light years until they hit the Earth with this cataclysmic response.
How does that bear out? Is this true?
Well, it's sort of it's still considered one of the explanations. The universe was much smaller in Fermi's day than it is today.
Yes.
Okay. And there were a lot of things that he didn't know about, and astrophysicists didn't know about, that we know about today. Black holes and black hole collisions and mergers, neutron star mergers, and all sorts of phenomena that quasars, all sorts of phenomena that emit particles and emit radiation. And so I think, no doubt, some of the energy that's imparted to these, incredibly energetic cosmic rays comes from those phenomena.
Right.
But there are, astrophysicists will say there are certainly magnetic fields out there that serve to whip and drive these.
This is a whole field for those at home. It's called astroparticle physics.
Yes, it is.
I did minimal work in the field under Stefano Profumo, and I didn't accomplish anything. So.
Oh well.
Well, actually, the interesting part was it turns out that to first order, it's really my work on linear polymerization kinetics seemed to use the same mathematics as primordial black hole merger events early in the solar system, because it's just things of one size merging with a thing of another size, and the rates at which they're doing that, and the rate at which
they're circling each other, and then they merge.
So if you ignore all the circling and you just want bulk mergers early on.
Oh, okay.
You can work out the statistics of what that statistical distribution would look like by using the same program, the software that I wrote for one of I don't know where that ever went. They had to correct a bunch of things because they had to add in a bunch of like the cosmological constant and a bunch of things that I wasn't really hip to at that time, and nor did I ever choose to become hip to in a strong way. But it was kind of fun. Any last pieces of for the viewer to walk away with when they're well,
I think
of course, buy your book, but what else?
My book is called The Last Man Who Knew Everything: The Life and Times of Enrico Fermi, Father of the Nuclear Age. I think I think this, to go back to solutions and ways to approach problems and solve them. I think Fermi's approach is really a model for people to try and use to strip away extraneous material and try to get to the fundamental of the problem and get a quick estimate of the solution without worrying too much about the precise solution, at least at first. Sometimes getting the precise solution is going to be really important. There's no doubt about that. But to sort of get the first order solution quickly can often be very insightful and give you a hint at what the precise solution looks like. And so I think that is a very important insight into problem solving and solutions. So.
Interestingly, that's, I think, maybe you'll agree, a skill that is actually maybe most important for people in business.
Yes, absolutely. Absolutely. Important for people in business, important for people in a lot of different walks of life. It's not.
I know as a consultant, I use this all the time because
if you often a business won't require a precise answer to a question. It will require a general answer to a question, like if you're losing money, are you losing money because your payroll's too big, or your cost of goods is too big, or one thing or another? And often, just sort of identifying the important factor is all you really need to do, and then the solution just pops out.
Well, it's another reason is because in business, every decimal point after doesn't matter as much.
That's correct.
Right? Because now you're talking first you're talking about millions of dollars, then you're talking 100,000. That matters less. Next line is tens of thousands, which matters less.
That's correct.
Once you get down to $100, you're talking about a meal.
And it turns out orders of magnitude are really important, right? I mean, there's a big difference between 10 to the 18th and 10 to the 19th. There's a very big difference.
Huge difference.
Between 10 to the 18th and 10 to the 19th. Not so much of a difference between 10 to the first and 10 to the second.
Right.
Not that much.
Exactly.
We can live with that.
Exactly. Well, thank you very much for coming out today. I appreciate you spending your time with me today.
Oh, it's a pleasure. It's a pleasure. And I hope we can do this again sometime.
I look forward to it.
Great. Okay.
All right.
Take care. Take care.
Excellent. Thank you for joining us this week on Solutions. I hope you enjoyed listening to it as much as I enjoyed making it. Please like and subscribe, as well as follow on Spotify and rate and follow on Apple Music or wherever it is you get your podcasts. I look forward to seeing you next time, and am excited to announce the launch of my Patreon, where you can actually start to contribute so I can make these videos. It takes some amount of financing in order for me to hire an editor, which I've had to do recently. And it is, there are expenses essentially associated with this podcast. So if you could donate any amount that you're capable of doing, if you're in that sort of a position, that would really help me out. And I also have a Discord, which I will be posting this episode to, and we'll be hosting a discussion for at some time that I'll specify. So stay tuned for that. And I will put the link in the description for that. Anyway, have a wonderful week, and thank you so much for listening. Signing off, Mason Hargrave.